Good afternoon and welcome to Algorithms and Data Structures today. We're doing a double lecture today because we had less students in the lab because we have this long weekend, even though today is an official lecture day. And next week we will not have labs and we will have no lecture next week because I'll be away all next week at a conference, but you have seen this already in iLearn. Last week, we started looking into recursion. We saw that recursion is one way how we can do repetition in a computer program, which is totally different to using loops, for example. We saw the factorial function as one example, and we saw we can implement it through a loop, but we can also express it in terms of itself. So the factorial function is n times the factorial of n minus 1. So it's a recursive definition. We've implemented this. We looked at the stack trace of recursive calls. We looked at the sequential search or linear search and saw that this is O of n in order to find a value. And assuming the data is sorted, sorting is something we're doing in the next chapter. Then we can use binary search, and with binary search, we can always, in each step, we can halve the interval we're looking at. We saw how we can implement this, and the binary search runs in O of log n. Divide and conquer is a pattern for designing algorithms. So we take a big problem that we don't know how to solve. So we can split it into smaller problems, then solve these smaller problems, and then combine the solution. And this is a pattern used in binary search, but also in numerous sorting algorithms we will see in the next chapter. The Towers of Hanoi is a toy example, yet it's also an example of divide and conquer because we don't know how to move that whole stack, but we can try to move a smaller stack plus then the largest item at the bottom. And we saw we can solve this surprisingly in a few lines of code, but that algorithm takes an exponential amount of time. We compared recursion to loops. Recursion leads to cleaner code. For certain problems, it's more intuitive to think in terms of recursion. Recursion is very helpful for some sorting problems, for some tree traversal problems, but recursion leads to more memory usage because of the stack trace. If recursion is not implemented correctly, it may be extremely slow. It can lead to a stack overflow, and it's probably harder to debug. In order to speed it up, we saw memoizing. So we saw that we can, in Python, use this LRU cache, which stores for a specific input the output of the function. And then when we call that function, we don't need to recompute, but rather we read from that cache if it's computed already. If not, we compute it and then put it in the cache. We want to eliminate tail recursion whenever is possible. And yes, we can theoretically always convert between recursive calls and loops. They have the same expressiveness, they're equally powerful, yet doing this is probably sometimes not that easy. Then we wondered how we can determine the complexity of recursive functions. And for this, we introduced the concept of a recurrence relation in which we describe the behavior of our algorithm in terms of n, and we have a recursive call. Like for binary search, we will halve that space. So t of n is t of n half plus some constant work. And we have the base case when we only have one element left. And assuming the worst case, we want to find what is the complexity of this. And what we do is we apply the recurrence relation to itself over and over. So n half n divided by 4, plus in each recursive call, we add a 1 here, until our n is so small that we are in this base case. So we see a pattern, and then we solve for k, which describes how the number of steps we are doing in a recursive call depends on n. And then we plug k into the solution for k into the pattern from before, simplified, and then we apply the O analysis to these terms. And then we actually have found the O complexity, the worst case complexity of the algorithm. So for binary search, that's a logarithm amount of time. It's something we also said that we would later see this in the lecture, as what we said last time, and we then saw why the binary search is actually O of log n. We saw another algorithm, which is a pattern of a class of algorithms that we will see more often, and we saw how to solve this recurrence relation. And I tasked you to look at a couple of other recurrence relations and try to solve them. The solutions are also in the slides. And then there was a list of further recurrence relations, for example, for sequential search, for a tree traversal, the towers of Hanoi, and you're most welcome to solve them at home as well in order to see if you find the O solution. Then we finished at this slide here, and I will discuss this slide with you now in greater detail. And for this, I'm switching to the iPad. So I introduced a function, and this function is called a of n, and the function is 1 when n is 0, 1, 2, or 3. So we say n is in that set 0, 1, 2, and 3. And then we said and we don't allow negative n's. And for larger n's, we say the result of this function is a of n minus 1 plus a of n minus 2 plus a of n minus 3 plus a of n minus 4 for n's that are greater than or equal to 4. Then I said last time there was a typo. Unfortunately, there's no typo. I made a tiny mistake because I was too excited last time in the lecture because I had already jumped into the recurrence relation mentally. But this is not a recurrence relation, so there's no typo in here. But I quickly want to show you how you can determine the O complexity of this algorithm. I asked you to think about this kind of stuff at home. Does any of you have a clue or suggestion what the O complexity of this algorithm could be, or of this function? So it's heavily recursive because we have a recursion here, there, and so forth. If you think you have a guess for the O complexity, maybe send me a positive reaction, like green reaction, thumbs up. If you don't see the solution, negative reaction. So I'll show you how you can determine the O complexity of this. So we need a recurrence relation. So the recurrence relation is the following. We have a base case, T of 1 is 1, and this is just for small n's. So we don't need to define T of 2 is 1, T of 3 is 1, but just for small n's, it's 1. It's just constant work, and we are done. But the T of n is now more complex because we see that there's some relation. It's T of n minus 1 plus T of n minus 2 plus T of n minus 3 plus T of n minus 4. What's important is that we add a 1 here, so plus 1 for the recurrence relation, because there is still constant work, because we need to do, for example, these subtractions here. We need to add all of this together. So there is constant work, and this is what this 1 stands for. So we could say that this is T of n. So T of n is T of n minus 1 plus T of n minus 2 plus T of n minus 3 plus T of n minus 4 plus some constant work. But solving this recurrence relation is not straightforward at all. It's probably quite tough. But remember, we want the O complexity, and O is an upper boundary. Maybe we can find a function or a recurrence relation that is above this one, and we can find for that for that simpler recurrence relation that is above this one, we can try to find the O complexity. So we can say this term is actually less than or equal to 4 times t of n minus 1 plus the constant work. Because we say t of n minus 1, t of n minus 2, t of n minus 3, t of n minus 4. And that is obviously less than or equal to 4 times t of n minus 1. Plus we have the constant work. And this is actually our recurrence relation. So the one in red is our t of n. And this one is greater than or equal to the initial one I had put there in blue. And for this one here, the one in red, we can try to find a recurrence relation quite easy. Last week we saw how we can solve recurrence relations, and we can apply just the same scheme. It's not a division, but a minus, so we subtract, and we have to keep subtracting in the pattern until we come to this base case. You can try this out at home just by finding the pattern for this recurrence relation. And remember, we want an upper boundary. This is what the O of n, or what the O notation stands for. And if we find the O complexity for a recurrence relation that is greater than or equal to our initial one in blue, then that's fine. Maybe we're not finding the exact boundary, but it's an upper boundary. And solving this one here is far easier because we just have to try finding a pattern for this one in red. If you do this, so you can try to solve this one at home, then this is O of 4 to the n. So feel free to use this one here in red. Find a pattern if you apply this recurrence relation over and over until you come to the base case, have your term simplified, and then try to find the O complexity for that term. And it will be O of 4 to the n. It's not the exact boundary of this one here in the blue one, but it's an upper boundary. And for this one in blue, you just don't know how to find a proper boundary. So find an upper boundary. So this is my advice for this problem. And this +1 here is very important because of the constant work that you're doing for doing these additions, the subtractions, and so forth. But the +1 applies to the recurrence relation, not to the definition here. So this definition is fine as is. So do you feel this has helped a little bit, giving you this hint, finding we found an upper recurrence relation or one that is greater, and then that's the trick. And then for that greater recurrence relation, you're trying to find the O complexity. Maybe just confirm with some reaction if you found this explanation helpful for solving this one here. It's still a bit of work, but we also have our phenomenal teaching assistant. Maybe she discusses such problems with you in the tutorial as well the coming weeks. And sometimes I've put stuff like this in the exam, which is not easy, but you get proper practice. And we've just seen the initial idea how to solve it, and make sure you try solving all of these common recurrence relations here. They are all not that difficult. These ones here, these two more ones, they look a bit more tricky because you need to find this pattern and work with this sum sign, but eventually it's also not that difficult. And I put the solution here, how I try to solve them. Now, we saw solving recurrence relations is tricky, and it's manual work, and it's not that easy. Now, we could wish there was maybe some more general approach to solving recurrence relations, and it turns out there is one. It's the so-called master theorem. The master theorem is a more generalized approach for solving a certain type of recurrence relations. Very importantly, not for all possible recurrence relations, but for a certain type. And we will now look at that and we will see what that pattern looks like. So we have a T of n that must be of the following form. You must have T of n is some factor A, can be what that factor may look like, we will later see. But we've seen, for example, when we looked at the binary search, we saw this was just 1. So A is 1, you could just leave it out. And then we say T of n divided by B plus some term, f of n, so some term depending on n. For example, for the binary search, this one here would be 1, and this would be 2. So B would be 2 because we divide n by half, and this term would just be constant, not depending on n. So f of n is just the term of extra work that is done here. If you have a recurrence relation that fits into this pattern, and we have some base case like T of 1 is 1 or constant, whatever, then we can apply the master theorem to solve this. And so n is the size of the input problem. B is the factor by which the subproblem size is reduced. Remember, for binary search, we said n gets halved, so the subproblem is half the size. So B is that factor by which we divide. And A is the number of subproblems in the recursion. We've seen this other generalized algorithm pattern, and we tried to solve it, and we said this was 2 times this, because sometimes you just branch out into multiple subproblems. It's not the case with binary search, but with other algorithms. Like we will see lots of sorting algorithms in the next chapter, and they may break up the data into a left and right half, but then you work on both halves separately. So it would be 2 times this n divided by half plus some extra work. So very importantly, the master theorem is not a solution to every possible recurrence relation, but to the ones that fit into this pattern. And now it turns out there are 3 cases in the master theorem. It's eventually how A and B relate to each other. And based on how they relate to each other, we need to pick one of those 3 cases in the master theorem. One thing is very important is, so I've just said this, there is a base case like T of n is O of 1 or even theta of 1, but here it doesn't make a difference. So we just have this base case. And one thing that we need to calculate initially is the so-called critical exponent, C critical. What is the critical exponent? Because I told you just before, we have 3 cases in the master theorem, and it's how A and B relate to each other. A is the number of subproblems, and B is the factor by which I'm reducing the problem, making it smaller for the subproblems. And depending on how A and B relate, we need to take a different case, especially when we condition on this f of n, which is this part here, related to a so-called critical exponent. And this critical exponent helps us to relate this A and B. Concretely, the critical exponent is the logarithm B of A. So the logarithm A divided by the logarithm of B. And if we just write this out, so a logarithm divided by a logarithm, then A is the number of the subproblems. Because we said we can branch out to 1 subproblem or 2 or 4, whatever. And B is the factor by which we divide the problem size for these subproblems. So we can say we're dividing the logarithm of the number of subproblems by the logarithm of the relative subproblem size. But A and B are just integers, so you can calculate this logarithm quite easy. We will now look at the first case of the master theorem. I have to tell you, when you sit the exam, so the exam is in 2 months, you don't need to know these three cases by heart because we're not talking much about the exam yet because it will come in 2 months and we will have also a practice session for the exam by discussing last year exam. But in my exams, you can take a one-sided A4 note sheet with handwritten notes. So what a lot of students do is every year in this note sheet, they write down these three cases of the master theorem. It's something I would personally do too. So you don't need to study this by heart. You need to know how the master theorem works and how these cases work. But the exact definitions you can just write on your note sheet. So it's a one-sided A4 note sheet with handwritten notes. And now in the case one, we're trying to relate this A and B together. So also when conditioning on this f of n, which is the work done in our current function call. And the case one describes where the work of splitting the problem and recombining is dwarfed by the subproblems. What does that mean? So we have work for splitting and recombining the solutions, but we split out to a certain number of subproblems. And case one addresses where this work on splitting and recombining a problem is dwarfed by the work in the subproblems. So we say this recursion tree is leaf heavy because most of the work is done in the recursion. It's not done at the upper level where we try to split and recombine. And the exact condition on f of n is in relation to the critical exponent. We say f of n is O of n to the power of c, where the c must be less than the critical exponent. You remember the critical exponent was this log b of a. And here we say f of n is O of n to the power of c when this c is less than the critical exponent. If this holds true, then in case one, we can say t of n is theta of n to the power of c critical. I know this looks very theoretical, so the best thing is we're looking at an example and we are applying the master theorem together now to a recurrence relation. And then you will see the beauty of the master theorem that will help us massively to. So I want to show you a recurrence relation for the master theorem where case one applies. So master theorem, case one. We have t of n is a times t of n half plus 1000 n squared. So this was this f of n. What are our values for a and b? If you remember from before, maybe tell me now, turn on your mic or tell us in the chat what you think are the values for a and b. Either in the chat or turn on your mic as you wish, but I'd like to include you in how we solve now this recurrence relation with the master theorem. Because you can try solving this manually with the tools from last week, but it's not going to be that easy, to be honest. With this master theorem, we solve it in a more structured way. So A is 2, A is 8, and B is 2. So, and our f of n is this 1000 n squared. So this also leads to, so we say f of n is O of n to the power of c, where c is 2, because f of n is this term here, 1000 n squared. So it's O of n squared, so n to the power of c is 2. What we need to compute now is the critical exponent. And the critical exponent, so C critical, is log B of A. So it's the log 2 of 8, which is 3. And 3 is greater than C, because C is 2. And now we have fulfilled the conditions of case 1 in the master theorem. So we said in the definition that T of n is theta of n to the power of C critical, which is theta of n to the n cubed, n to the power of 3, because this comes from here. So we see for our recurrence relation, which is T of n, A times T of n half plus 1000 n squared, eventually the complexity is theta of n to the power of 3. You could try to solve this here manually if you wish, but it will take you some more time than with the recurrence relations we have studied before. And it's probably more work and not that exciting to solve this manually. So rather use the master theorem to do this. And feel free to apply the master theorem to all these recurrence relations from last week if they are actually suitable for the master theorem. So, and the beauty is also we get thetas, not O's. So thetas are actually preferable. This case 1 example is also in the slides, and there's a case 2. The case 2 now assumes or is for when the work for splitting and recombining is comparable to the work in the subproblems. Because before we said most of the work is actually done in the subproblems, because the work for splitting and recombining is dwarfed by the subproblems. Now, the work that we need for splitting and recombining is comparable to the work in the subproblems. What we need to calculate is, again, the critical exponent, which is just log B of A. And the case 2 also says the condition of f of n is f of n is theta of n to the power of C critical times the log n raised to the power of k. So this one you need to read out as you calculate the logarithm of n, and that result is raised to the power of n. But this only works where k is greater than or equal to 0. And if this condition holds true, so how the critical exponent relates to f of n, then the master theorem says our recurrence relation is theta of n to the power of C critical times the logarithm of n raised to the power of k plus 1. And I think here it will make sense again that we look at an example together and try to solve it. So, case 2, we will have T of n is 2 times T of n half plus n. Do you remember this recurrence relation from last week? If you remember it, because we studied it, maybe you sent me some positive reaction. If you remember it, also, maybe you remember its solution, or you can just go back to your notes from last week and tell me what you think the solution was from when we solved it together, because we tried to manually solve this one, which was quite some work. And now with the master theorem, we can solve it in a more structured approach. No one seems to be remembering it, so it would be good if you send some reaction if you remember it, as well as if you remember the solution. So A is 2, B is 2, and f of n is n. now we say f of n is theta of n to the power of c critical times the log n raised to the power of k. Is our f of n of this nature? Yes, it is, because we can say this holds true when this critical exponent is 1 and k is 0. So I would put a 1 up here. And if I raise the logarithm of n to the power of 0, it's just 1. So this whole log term would just be 1. So we see our f of n is actually described by this theta here, because the critical exponent would be 1 and k would just be 0. So this term here would just become 1. We can calculate now our critical exponent, because only if that's the case, then the f of n fits in here. And the critical exponent is always computed exactly the same in these examples, in the 3 cases. It's a log b of a, so it's the binary logarithm of 2, because a and b are both 2, and that's 1. So holds true. Because this one here would only work if the critical exponent is 1. And in fact, it is. So it follows from the master theorem, as we defined it in case 2, t of n is theta of n to the power of c critical times the logarithm of n raised to the power of k plus 1. This is what we saw in the definition before. And now we can just plug in our values for k and the critical exponent. So we can say that this is theta of n to the power of 1 times the logarithm of n to the power of 1, because our k is 0 and we say k plus 1. So we have n to the power of 1 times the logarithm of n to the power of 1. So we just remove these ones. So it's n log n. And the result, do you think the result is correct? Does it match the result to when we solved this recurrence relation manually? Do you remember it? Please send some reactions, because I see your names. Some of you were in the lecture last week. Which result did we get for this recurrence relation when we manually solved it? It was, in fact, n log n. We said O of n log n. Here we get a theta. So this answer here is actually correct. And it works in a much more structured way, because we just apply the master theorem rather than trying to solve this manually. And just to be on the same page, it was this example here where we looked at this algorithm pattern and we said this is the recurrence relation 2 times t of n half plus n plus the base case. And we tried to find the pattern, solved for k and plugged k in, and we got O of n log n. And now with the master theorem, we actually have a much more structured approach rather than trying to manually solve this, but we just follow the rules of the master theorem. These rules, I have to admit to you, if you randomly approach me, I probably also don't fully remember each of these terms. And that's why for the exam, probably you would just write it down on your notes sheet. So I don't expect you to know this by heart. And the one we've just solved together on the whiteboard is also here again, well formatted. There's another example that you can try at home. It's actually the one for binary search, or a recurrence relation for binary search, or this kind of algorithm where t of n is a is 1 and b is 2, so n gets halved plus some constant work. And you can also see that this actually falls into case 2 and eventually we get a theta of log n. But feel free to do this exercise at home. The solution is also here, and you will see that it actually works very well. So it works much simpler than trying to solve this recurrence relation manually, and you actually get a theta, which is also an advantage over the O. Now, we've looked at two cases. Case 2 is the work for splitting recombining is comparable to the work done in the subproblems. We've seen case 1, where most of the work is done in the subproblems, not the splitting and recombining. So the last case possible is case 3, where the work for splitting and recombining dominates the work done in the subproblems. And this one, we would say it's root heavy because most of the work is done in our node in the tree rather than in the leaves in the subproblems. And here the condition is f of n in relation to our critical exponent. F of n must be omega of n to the power of c. Remember, omega is a lower boundary. But this time we require that c must be greater than the critical exponent. If you study the master theorem in detail, you will see that this, however, does not yield anything yet because this is a lower boundary. But we need a further condition, and this further condition that we must satisfy in case 3 is that a times f of n divided by b must be less than or equal to k times f of n, where this constant k must be less than 1. If we find a k that is less than 1 that satisfies this constraint, then we can actually use case 3. And for case 3, it's super simple that our t of n is theta of f of n. We will again study an example together, and then we've done most of the tough math for today. So we will do case 3. And for this, I have another recurrence relation. It's t of n is 2 times t of n half plus n squared. So a is 2, b is 2, and f of n is n squared. And we see that f of n is our omega of n to the power of c, where c is 2. So n squared is a lower boundary of n squared. And now let's see if we actually satisfy case 3 and its conditions. So the critical exponent is log b of a, and that means again the binary, don't know where this 1 came from, the binary logarithm of 2, which is 1, and 1 is less than c, because c is this 2. Now we still need this one more condition to hold true, and this condition to hold true was something like we said that our a times f of n divided by b must be less than or equal to k times f of n, where k is less than 1. So let's see if we can fulfill this. Remember, a is 2, b is 2, so, and our f is just n squared. So we can just plug all of this in. We can say 2 times, so a is 2, f of n divided by 2. This is, so we just plug n squared now into f. So we can say it's 2 times n half squared, because the function f just squares. So we can say 2 times n squared divided by 4, because we just square this term and this term. And this one is less than or equal to k times n squared. So we have this k and this f of n. When we choose, so this holds true for k being a half. And k is less than 1, that's what we required. So we're in case 3. We're perfectly fine. We can say t of n is theta of f of n, and that is theta of n squared. So we have found for this recurrence relation, we have found the complexity, the running time complexity, concretely a theta, not an O. Feel free looking at these 3 examples. So we had this recurrence relation, then the one from case 2, one from case 1. Try solving them manually at home if you wish with the tools from last week, or simply use the master theorem. For the exam, you need to know both approaches. In the exam, if I just give you a recurrence relation and ask you to solve it, it's up to you which method you pick. However, if I give you a recurrence relation and ask you to use the master theorem, you have to use the master theorem. If I require you to solve it without the master theorem manually, then you have to do so too. So you need to know both. But if I don't specify the method in the exam, you can pick it. This was the example of case 3 we've just studied together. It's very important that your whatever recurrence relation you want to use for the master theorem needs to fit to this pattern here. A times t of n divided by b plus f of n. And there are a couple of examples here of recurrence relations where you cannot apply the master theorem. Something like t of n is 2 to the power of n times something. A must be a constant, but 2 to the power of n is not a constant because it depends on n. So the number of subproblems must be fixed. Here it's not fixed. So you cannot use the master theorem here. We have something like t of n is 2 times t of n half plus this one here. But because this is not a polynomial, you are also unable to use the master theorem here, where something like this t of n is a half t of n half plus n. Now a is less than 1, and that doesn't make any sense because you cannot have half a subproblem. You can have 1 subproblem, you can have 2, you can have 3, but it must be an integer and it must be 1 or greater than 1, but not less than 1 and not a float value. So here you cannot apply the master theorem. This one here, theoretically, the f of n looks okay, but you have a minus. And the combination time is always positive, not negative, because you cannot just reduce running time. So this one here also doesn't make any sense because it's negative. And stuff like this also does not, it would look like case 3, but we have this regularity condition and where we said we have this inequality in there, and this one here does not satisfy it. So all of these equations here are not working for the master theorem. I want to double check with you. We had this huge list of recurrence relations. Can you apply the master theorem to this one here? I want to see from you if you think we can apply the master theorem here. Thumbs up or green sticker. If you don't think so, negative reaction. I'd like to see some more responses, please. So positive response. Yes, we can apply the master theorem here because we have an A, a B polynomial difference. Can we apply the master theorem to this one here? T of n is T of n minus 1 plus 1. If you think so, a positive reaction. If you don't think so, negative reaction. I'd like to see some more responses. So you think we can apply the master theorem here, but one student disagrees. The one who disagrees was actually correct because you always need to divide the n by something. You cannot just subtract something from n. So the master theorem would not be applicable here because we always need to divide n by something. This one here, we also cannot use the master theorem, or this one here also doesn't work. So the first one works, the third one, and the fifth one. And here, the master theorem also doesn't work, by the way. So always make sure that your recurrence relation fits into this pattern, and then you can use the master theorem. Otherwise, you cannot. Now we are almost done with recursion, but there are three concepts left, or two concepts left, but one is bigger that I want to discuss with you. There is a term that you often come across when you study algorithms, and that term is backtracking. What does backtracking mean? Imagine you want to solve a maze. You go from the entry to the exit, and you move forward, and you can move forward. But at some point, maybe you have reached a dead end in the maze. So what you're doing is you're going back to your previous state where you still had an option to go somewhere else. Maybe you had turned left at some point in your path, then you go back to that junction and you turn right and you try and keep walking. This is what backtracking means. Backtracking means you're trying to solve a solution, a problem and find its solution, or maybe it has multiple solutions and there are certain constraints, but when you get stuck, you're unable to continue with that candidate, then you're going back to a previous solution or part of a solution from which you can still move forward. So you would backtrack and abandon a path and then continue with a different action in the previous state. This is what backtracking means. And backtracking can be applied, for example, for solving a maze, but also for lots of other optimization problems. The backtracking algorithm is something that is studied in great detail in a lot of algorithms and data structures courses. It turns out we have studied that already at the very beginning of the course when we looked into graphs. But there, we did not call it backtracking, but we talked about shortest path and lowest cost. Technically speaking, backtracking is something slightly different to the shortest path and the lowest cost, but we have done more or less that already with our highly generic algorithms, shortest path and lowest cost. That's why in this course, we only have one slide about backtracking, just to quickly introduce the term in case you come across it. Maybe I have even used it in the lecture when we talked about shortest path and lowest cost, when we go back and try a different action. But we're not discussing this generic backtracking algorithm now in detail because we have done something quite similar already when we looked at graphs. So small topic, just the terminology. If you hear backtracking, that you know what it means. But we will now look at a different concept that helps us to speed up recursion. We have done this last week already, and we studied how we can speed up recursion, and we had done this by using this decorator where we put this LRU cache in front of the in front of a recursive function. And I told you last week we would study how this exactly works. There's a question about merge sort. So merge sort is a different algorithm that we will see in the next chapter. So we're now in speeding up recursion. Merge sort does something quite different, but maybe in an hour or so we will see merge sort, and then maybe we can come back to the question here in the chat. Dynamic programming, more from a very generic perspective, is a mathematical optimization method and also a computer programming method. For example, in operations research, it describes a huge set of methods to or for mathematical optimization. We will also use dynamic programming now, but in the context of recursion. And what it does is it allows us to solve recursive problems faster. And there are two approaches of how you can speed up your recursion through dynamic programming. Either it's a top-down or a bottom-up approach. And these are the two examples we will briefly calculate or briefly implement together. So for this, I will share my live coding session. We will start with the top-down approach. Remember, last week we implemented the Fibonacci function, which was something like Fibonacci of n, and we said, I'm just going back to code it exactly the way we coded it, so just jumping back a few slides. We said the Fibonacci of n, where n is 0, we return 0. When n is 1, we return 1. Otherwise, we return the Fibonacci of n minus 1 plus Fibonacci of n minus 2. And we saw running this for already sufficiently n, it will be super slow because we have this branching recursion. And we had put this LRU cache in front of it, trying to speed it up. And I'll show you now how you can speed this up without using this LRU cache, but by building your own cache. And then we'll see how it works. So what we need is a memory. And the memory will be represented by a dictionary. And for this, we put initially the base values for the Fibonacci function. So we said if n is 0, we return 0. So we have the key is the input and the output is the result. And when n is 0, we return 0. When n is 1, we return 1. And now we can try to implement the Fibonacci numbers again. So Fibonacci top down, just write it out, top down of n. What we can say is we want to check if our n is in the memory. And if it's not in the memory, we're going to compute it. So we can say if n is not in the memory, and what Python does here is it checks if this n is available as a key in the dictionary. We've introduced dictionaries like 2 months ago when we started with Python, and these dictionaries are key value stores. In like 3 or 4 weeks, we will start implementing our own dictionaries. We will see how they can be implemented on our own, but for now we still rely on the Python dictionary. And we see we have a key and a value. And we've seen these dictionaries also when we built our shortest path and lowest cost algorithm. And we saw that these are not necessarily integers. We can put in different objects. We can have also tuples as keys if we wish with so multiple entries per key and so forth. So it's all possible. And we're checking now if n is not in the memory. If so, we're going to compute it. We say it's fib top down of n minus 1 plus fib top down of n minus 2. But we are not just returning it, rather we are adding it to our memory. So we can say memory of n. So we are storing for entry n, the key for the key is n. We are storing as the value the result of Fibonacci top down n minus 1 plus Fibonacci top down n minus 2. And then we are returning our memory entry. And what we're doing is here, we have just built our own cache, because this now is in a global context. And when I'm calling fib top down on 0, it just returns 0. It just checks here, is this in the memory? And it is, so this line is ignored and we're just returning from the memory. The same for 1. If I'm running this now for 2, for example, it will look it up and it will see it's not in the memory. Then it computes this by calling fib top down for n-1 and n-2, summing it up and storing it in the memory and then returning it. The result is also 1, but we will see the memory has been growing. A new entry has been added to the memory. And it's similar now if I call this, for example, for 8, the result is 21, and the memory has been growing. This is not as efficient as our LRU cache, because the LRU cache decorator that came from Python makes also sure the cache doesn't get too big and so forth. But here it's just very small objects. It's just integers. If you store very large objects in your cache, you may want to manage the cache differently, but this here doesn't matter. And it's super fast. Let's test this. So we have a fair comparison. So the memory will just be reset to its initial value. And we can use this time, and we said we call time fib on 30. So fib is the naive one. It doesn't use any caching, no tricks. And we see it took like 101 milliseconds. And we can call this now on fib top down, for which we have reset the memory. And we see it takes just 21 microseconds. And if you make n much larger, the difference will be even bigger. And we see the memory has grown because these new entries have been added. So what I have just shown you is how to build your own LRU cache. It's not an LRU cache. We've just built our own cache. And it's maybe not as universal, especially if you have multiple parameters. You could have a function with multiple parameters. I mean, you can customize this and you can use tuples as keys. It's all possible. The LRU cache is highly generic, so it already does that for you. But what we have done here is a top-down approach. So we called it fib top-down. And it's eventually just the direct consequence of the recursive formulation of our Fibonacci number problems. And what we do is top down. We are starting with the large n, and we increasingly break it down to smaller n's until we can compute these small n's. And then we go back up in the tree and we combine all the results. So it's a top-down approach. We're starting with the big N and we're going recursively down, compute the small n's, and then recursively put it back together. And we can see just by using such a simple cache, it becomes massively faster. And adopting this to multiple entries is not that difficult, by the way. The other approach is a bottom-up approach. And oftentimes you will see this in algorithms that when you have a computational problem, there's a top-down algorithm or a bottom-up algorithm. We will see this, for example, with sorting today as well. We will see some sorting algorithms that are top-down and some that are bottom-up. And here for our dynamic programming, to speed up our Fibonacci numbers, we can also build a bottom-up approach. And the bottom-up approach works the following. We start by calculating the solutions of small problems, and we keep increasingly merging or combining them until we have reached a solution for n. So we are not taking the big N and breaking it into smaller n's, but rather we are starting directly with small n's, and we keep increasingly combining these solutions until we have reached the desired problem size. And then we stop. And we can try to implement this now for the Fibonacci numbers as well. We can say this is a Fibonacci bottom up. And this one here even doesn't need to be recursive, because what we are doing is we will just start with these very small n's, and we keep adding always the next Fibonacci number on top until we're done. And I'll show you this. So it's bottom up, and we say we need a edge case where n is 0, we just return 0. And now we have two helper variables, and we will use a loop to incrementally build larger and larger Fibonacci numbers. We will have the previous Fibonacci number. So if we start with 0, we are done. We return 0. If n is 1, we need one exception that you will see now, because we have our current Fibonacci number. That's the one we would actually wish to return. But this special case where n is 1, we will see very soon. Let's assume n is now a little bit bigger. So we start with the two initial Fibonacci numbers, previous Fibonacci and the current Fibonacci numbers, 0 and 1. That's also the ones we see here in the values, 0 and 1. Then 1, 2. So a Fibonacci number is always the sum of its two previous ones. So the 5 is the sum of a 2 and 3, the 13 of 8 and 5, and so forth. So what we want to do now, in order to have the next Fibonacci number, we can say next Fibonacci number is the previous Fibonacci number plus the current Fibonacci number. But we need some sort of repetition in here now, because n may be very large. So we can say for index in a range of n, I want to calculate this next Fibonacci number, which is the sum of the previous one and the current one. And because I want a fixed number of helper variables, I need to rotate these values now, because I have calculated the next Fibonacci number. What I don't need is the very beginning one, because now I have the current one and the next one. So I don't need the previous anymore, but I still need these variables. So I will say my previous Fibonacci number is now the current Fibonacci number, and my current Fibonacci number is the new Fibonacci number. And then this loop keeps running until I'm done. And I can return the current Fibonacci number. However, there is still one tiny bug. It doesn't work this way. I need to put in n minus 1. And I'll tell you why. If I put range of n, it will run up to n minus 1. But I have two helper variables, and if I put in n in here, it will run up to n minus 1, but it will add one Fibonacci number too much on top because of two helper variables. So what I need to do is I need to put here n minus 2, that the loop runs and includes n minus 2, and I have these two helper variables that I add together. So only one quick hint for Python. It has nothing to do with the algorithms course, but with Python. I want to show you a quick convention in Python. I have this index I, but I don't use I at all in the loop, because I just need a loop that is running, but I don't need the index variable. I could use a while loop or some other stuff if I wish, but then I would still need a counter. If you have a for loop in Python and you don't need the index variable, you can just keep it I, but if you use some static checkers or some IDE support tools, then this will still be shown to you that you have introduced a variable that you're not using. So a convention in Python is, if you have in a loop or somewhere in your code a helper variable that you don't need at that moment, oftentimes you just denote it by underscore. This is a valid variable name. Maybe it doesn't look that fancy, but if you use these helper tools in an IDE, it will be ignored and you won't get bothered. Also, one quick note. I'm very happy you sent all your course evaluations, and they have been largely very positive. So, thank you very much. There were a few things I quickly want to address. Two students wished I should use an IDE to do the live coding sessions. There's a reason why I'm not using an IDE, because in the IDE we have all these helper tools, and they will always highlight a lot of stuff in our code, which will largely just lead to a lot of visual distractions. And an IDE that we are using would, like, for example, PyCharm would run our code in batch. But I want an interactive session. So I can build these algorithms step by step with you. And if I run this in a batch mode as a script, then I only run it once and it terminates. So I want to actually use this. I could obviously use the Jupyter notebooks, but again, they add a lot of visual distraction in a browser. So this interactive Python session here just doesn't provide distractions. And I also don't want to rely too much on the IDE here because I actually want to get things done and I want to learn how this works. If you build professional code, obviously you're welcome or you should be using IDEs. But I'm telling you, when I start building my own algorithms, the first thing I'm doing is I start building this in an interactive environment because maybe one line works, one line didn't work as expected, but I still have some old state I can go to and I can reuse it. And then when I have a draft of my algorithm, I just do an export into a Python file, which you can also do in here. So I like this interactive mode to step by step build my algorithms and keep some lines that are helpful, quickly kick out some that were not that helpful. And if I do this in an IDE in a batch mode, it will take much, much longer and be probably way more complicated. So if you're not familiar yet with these interactive modes, use them. You will love them, and they will definitely make your life easier understanding the programming language, building your own algorithms, and so forth. So this was one thing raised in the evaluations, and but overall the evaluations were very positive. Thank you very much. And there were a few other smaller points, but I know it's a lot of workload, and we have this double lecture today, but next week we don't have lecture. And we already missed quite a lot of Fridays because there are some more public holidays later in May and June on Fridays, and we will not do double lectures on those public holidays anymore. We did that once just to speed up a little bit more, so you also have more content for the tutorials and so forth. But there will still be a few Fridays that we miss because of some lecture-free days, public holidays, whatever. And I'm just quickly checking the course evaluations if there was, because this just came to my mind with the IDE now. There was maybe something else in the course evaluations that I want to see. Yeah, the IDE was raised a few times, and there's a clear reason why I'm not. And one person also raised why we use simple variable names, not more meaningful ones. There's a reason for this. It's not a software engineering course. We simply often want very short variable names, so it fits on the slides. And I know when we introduced for example, the array list, which is called the array capital A, just to keep it as short as possible. I know in a software engineering course, programming course, you would use more meaningful names, but I want all of this to be very short and fit on the slides. And this is not a programming course, it's an algorithms course. So big difference, but we can also test this now. We can call, so this is the bottom up, and bottom up it's called because I start with these initial numbers and then I keep adding them together and creating the next Fibonacci number until I'm done. So I'm not starting like up here with the top down. Both of this is top down, but the top down we had used here was we used the top down here and we were speeding it up because of this cache. And here with the bottom up, we are starting with the initial numbers, and then we keep increasingly combining them. And this one here, it also turns out, gives us just the same result. So we can say the bottom up of 30 should also, and there was one typo. It's not called, it's up here, not called next fib. It's called new fib, which is correctly done in the slides. So it's new fib, and then I'm assigning the new fib here, but now it should work. Slides, it's correctly. And we see it's the correct value. It's 832,000 and 40, like with the Fibonacci number top down of 30. And so they give us the same result. We can do a test and see which one runs faster. What do you think, which one runs faster? We will reset the memory, and we will run this. Let's start with the top down for very large, let's say 200. What do you think, which one runs faster? If you think top down runs faster, green reaction. If you think bottom up runs faster, red reaction. So green for top down and red for bottom up. And a few more reactions. So there's a majority green that students think top down runs faster. Let's test it and let's run it for 200. So it takes 118 microseconds. I personally would assume the bottom up runs faster, but let's see. The bottom up actually runs 6 times faster approximately. So the bottom up takes 19 microseconds rather than 118. And I'll also tell you why this runs faster. So the bottom up is extremely fast because I have a fixed number of helper variables, so fixed space. And I have this loop here. Well, I have this range, but I need some repetition anyway. And all I'm doing in the loop is I'm adding up values, shifting values, and I return it. This is O of n, obviously, because the loop runs, but it's extremely fast. And there's no recursion. And I told you recursion may be slow, and each recursive call leads to some extra work on the stack, because I always need to put something on the stack in the operating system. And here I don't need to do this. I only have one function call of the bottom up. But in my top down, I have recursive calls. And I have them here. And eventually, yes, I'm not doing duplicate work anymore, because when I'm calling this recursive call, it may very quickly check then in the recursion in the memory and always return from the memory as quickly as possible. Yet I have recursive calls, and maybe after the recursive call, I quickly have a memory check, but it's still some extra work. So it is slower. We see just some factor, not in a different polynomial, but it is slower because I always need to check still something. And I need to put something on the stack. And doing these memory reads, it all takes a little bit of time. While here, with the bottom up, I don't have that problem. So the bottom up is much faster. We could combine this bottom up also, if we wish, I don't know, with a memory. So the advantage of this one is we have a memory, so we don't. So if I run this once on, say, 10,000, and it's computed once and stored in a memory, but this one here, if I call it again on 10,000, it would recompute it again. And that's why before I had reset the memory just in order to make sure it's a fair comparison. And I actually noticed I made it, well, we'll run it again. I noticed just from the copy and pasting, I called this B memory and not memory. Even for the memory was small before, only 30, but there was a typo. We'll test it again. So the top down is now 127. So you see there was a minor difference, but we could also time it and run it multiple times. because now it's the correct memory that was reset. And we run this bottom up and it's still 19. And so before we had with our mistake, because part of the memory was not reset, or the memory was not reset, but it was only set to 30. So the difference was negligible, yet now the difference is even slightly more because we've now set the memory correctly back. And we can test it again and run this, say, the top down for, say, 1000. Let's see if this works. 506 microseconds. And the bottom up should run much faster. Yeah, so factor 5 here now. Obviously, if you go back to the original implementation and you call this inefficient implementation on 1000, it will not finish in your lifetime. And there's a question about the top-down if we don't calculate new values based on previous smaller ones. So the question is, so I put in an n, a new n, and it will check, or some n, and it will check, is it in the memory? If so, it will read it. If not, it will calculate it from two recursive calls. Say we have in the memory everything up to 1000. And now I call this on 1001. 1001 is not in the memory, so it does a recursive call on the 1000 and the 999, so two recursive calls. But this one here, in the recursive call, we'll see that 1000 is in the memory, the 991 as well. So these smaller parts then don't get recomputed because they're in the memory already. If they were not in the memory, they would also have to be recomputed recursively. And we would end with the ones that are in the memory, like these initial ones, or maybe even more if we have filled the memory before. So the top-down breaks the big N into smaller n's, keeps doing this recursively until we have n's that we can compute, and then increasingly recursively actually combine them. While with the bottom up, we are starting directly with the small ones and we keep combining them until we have reached the proper problem size n. So I hope this explanation helped. And I'm just quickly going back to our slides. So this is, we said there are two dynamic programming approaches, top-down, bottom-up. Top-down, I've explained, we've implemented it for the Fibonacci numbers, and bottom-up, I've also explained, and we've implemented it for the Fibonacci numbers as well. And we've also run some tests and saw how they compare to each other. And both approaches here allow us to massively speed up the Fibonacci numbers. If you use the naive one from last week that I had done in the very beginning of my IPython session, and you put in 1000, this will not finish in your lifetime, and it will run out of memory as well because you have too many calls that don't fit in your RAM anymore. So, when it comes to the coursework, I said last week already that we have coursework for recursion. All of these problems could have been done with last week's content already, but you have now a few more tools how you can maybe try to speed this up or how to determine the running time complexity. So there are a few small exercises from the book, and then I have something interesting for you that I have come across many years ago. If you have a power like x to the power of n, like 2 to the power of n, or 2 to the power of 10, in a naive way, you would calculate this by saying 2 times 2 times 2 times 2, so 10, until you have multiplied 2 10 times together with each other. So you would say x of n is x times x to the power of n minus 1, while n is greater than 0. And this is just a naive linear way to implement the power function. And here we just look at powers n and positive, so we don't look at like negative powers, whatever, it's or whatever. Don't want to do the fractions here. So So you say x times power of x where n is -1. You can implement this in a few lines of code and think about what the running time complexity of this linear one is, but I'm saying linear. In fact, this is O of n, and you can try to implement this recursively. You can try to turn this into a loop, but it will still take O of n. And you can come up with the recurrence relation. You can try to solve it and then see it's really O of n. So there's lots of stuff you can do here, and you can try also to implement it with a loop and then determine the running time complexity. And it actually turns out that you can speed up the calculation of the power function. When n is 0, obviously the result is 1. And say if n is even, so you say 2 to the power of 10, for example, you could say 2 to the power of 10 is 2 to the power of 5 times 2 to the power of 5. So you break this up recursively and you keep doing this. And then you only calculate the power of x to the power of n half once, and you would square it with itself. So you multiply it with itself. You need to implement this correctly. It's very importantly when you write your Python code that you calculate once the power of x to the power of n half, and you square that result with itself, and that you're not calling this function a second time, because if you're doing this a second time, it will still be linear, and in practice it will be even slower because of the extra recursion. If your n is odd, you also need to floor that value. So this here is the flooring sign. So you floor a 2.5, and that's a 2. And then you say x times power this recursive one squared. But you can test this out on a piece of paper, and you will see that this will run, if it's implemented correctly, much faster than your power here, especially when you make n very large. And you can think about the recurrence relation for this one here. It turns out it's a recurrence relation you have seen already a few times today and last week. And you can try to solve it either manually or using the master theorem. So there's lots of coursework. All of this could have been done with the content up to last week, but for especially solving the recurrence relation for this algorithm, then you can do this with the master theorem and see if you're coming to the same result. So there's lots of stuff for you to practice here. And since we have a double lecture today, we can already, and this is also in the slides, my bottom-up implementation, but that's just the same one we have done before. And we will now switch to the next chapter, which is sorting. The sorting chapter is put exactly in this part of the course for a very good reason, because I also want to highlight again why we're doing these chapters in this order in this course. We needed an intro, obviously, what the course is about. We needed to introduce Python. We looked at graphs as very generic structures and very generic algorithms, because all the data structures from now on, lists, trees, maps, and hash tables, they're just graphs with certain constraints. We want to build efficient algorithms and data structures, so we needed complexity analysis. Then we looked at lists as very constrained graphs, and we saw some algorithms on them and their complexity. And then we looked into recursion, which helps us to break big problems into smaller problems and combine all of this eventually by using divide and conquer. And today we will look at sorting, which helps us to bring order into our data. In the recursion chapter, we used also the binary search, and we said we assume our data is sorted. But it turns out discussing sorting without discussing recursion first doesn't work too well. So we need recursion first, but assumed that we can sort our data. But now we will actually see how we can sort the data. And sorting can be also, at least some sorting algorithms can be implemented quite well using recursion. And we will see recurrence relations again. Also, one note, I just wanted to say, I forgot this before. This better or more efficient definition of the power function is something I saw when I was a student in my first semester. The professor had not taught this, but I saw the professor had put this into one of the past exams because the professor also, when I studied, so my algorithms and data structures course was in my first semester in my undergrad, the professor also had a huge set of coursework problems on his website, was on the website. And I did all of them, and I saw this power problem, which was never discussed in class, but it was in this huge coursework pool. And in some past exams, it actually appeared, and I felt the students who had done this kind of stuff in the coursework probably performed better in that past exam. And what I had shown you here before is this dynamic programming for recursive functions. That's also something that that professor had put in past exams and had in the coursework, but had not discussed it at all in the lecture. And then it actually appeared in my exam. And fortunately, I had looked into all the past exams and the coursework. Um, I'm not behaving this way. I find this a very important concept, so I discussed them here with you in the lecture because I think dynamic programming is more than just referring you to the coursework, and we've discussed it. But please spend some time on this power function here because it is important and it will help you to revise some of the concepts we have studied today. Now, in the sorting chapter, we will look at increasingly more complex sorting algorithms. We start with the bubble sort as probably the simplest sorting algorithm. And then we will briefly look at two other ones, but they're also not that efficient. And then we'll look at merge sort and quicksort, two highly efficient sorting algorithms. Now, do you know any other sorting algorithms? Have you ever heard about other sorting algorithms? Because there are way more. If you've heard about some, maybe just raise your hand and tell us in the mic or send them through the chat. We'll see some other terms later about other sorting algorithms, but we are discussing the most important ones in the lecture today. So why is sorting important? Sorting is one of the oldest and probably best studied problems in computer science. Because when we store data in a database or some other format, typically we want to be able to search efficiently in these data sets. We've seen the binary search algorithm as a very efficient search algorithm, which runs in logarithm time, which is phenomenal. Actually, that's also the optimum. It cannot be, you won't be able to search in a better complexity class for that kind of problem. But in order for it to work, we need to store our data in a sorted way. And there are lots of other things or other data structures and algorithms that include sorting as part of this. For example, we will see trees. Trees can also help us to store data in a sorted way so we can search very efficiently in that data in a tree. It's something we will see in the next lecture. So sorting is something quite important because we want to store data sorted so we can search in it super efficiently. And it's part of lots of other algorithms, by the way, and data structures. Now, the simplest sorting probably is, well, maybe the simplest sorting possible is just a random sorting. It's called a BOGO sort. So BOGO sort just means you just shuffle your data random. So you randomly, you put your data in a random order and you check if it's sorted. And if it's sorted, you're fine. If it's not sorted, you just shuffle the data again and keep going. This is unlikely to be efficient and it's not guaranteed to ever terminate. If you have a huge data set and you just keep shuffling and shuffling and you hope it's sorted just by shuffling by chance, this is super unlikely. So that's a BOGO sort, not very good. Then A more reasonable approach, and it's probably also one of the simplest approaches, but one that actually works, is a bubble sort. And the bubble sort works the following way. Imagine you have a data set that is unsorted, and the sequence is 5, 3, 8, 4, 6. You start looking in your first step at the first two entries, 5 and 3. Are they in the right order or not? If they are in the right order, fine. If they are not, you swap them. And 5 and 3 are not sorted because we need the 3 first and then the 5, so we just swap them. Then we compare the second and the third element, 5 and 8. They are in the right order. Then we look at the third and the fourth element, 8 and 4. They're not sorted, so we swap them, 4 and 8. And then we compare the last two elements, 8 and 6, which are also not sorted, so we swap them. So we've done now one pass through our data set. We've swapped the 5 and 3, the 4 and 8, so 4 and 6 was here, but you see the 8 got moved to the fourth spot, which is here, because we've swapped 8 and 4, and then we compared 8 and 6, and we also swapped them. So in this first pass, we have actually moved the largest value, 8, to the right. And what we have now is 3, 5, 4, 6, 8. It's not sorted yet. All we have done is we have moved the largest element to the right, but the others are not necessarily fully sorted yet. So we need to repeat this procedure again. So we need to run again that we look at the first two elements, 3 and 5, they are sorted. 5 and 4, they are not sorted. So we swapped in 4 and 5, and then 5 and 6 are sorted, 6 and 8. And we keep doing this. We keep doing another pass until it's all sorted. And this is the idea of the bubble sort. It's probably the simplest reasonable sorting algorithm. And I'll show you now how we can implement this. It's fairly easy to implement. We can say we have a bubble sort, and we have a sequence A, say a list that we want to sort, and we need to know how many elements are in A. Then we have a loop, an outer loop. We say we go through, and this is now a very initial implementation. It's not the most efficient one, but a simple one. We can say we go through from I, that is 0, up to n minus 1. So we go through n times. But we also need an inner loop to do the actual swapping. So we say, again, an inner loop that is n in the range. And we can say, if the element at position HA, so with the inner loop, we do one pass of our data, but we need multiple passes through the data, and this is what the outer loop guarantees. And if the element at index HA is greater than element HA plus 1, then we swap them. Will come. Now, this will lead to a runtime error because J plus 1 on the last possible index will lead to an invalid index. So I need to put in n minus 1 in here, because then J plus 1 will be valid for the last index I get from the range. If I put this away, you can run it, it will not work. And now we see that element HA is greater than element HA plus 1. So the left element is greater than the right element. So we need to swap them. And swapping can be done, for example, this way. I have a temporary variable which contains the left value. Now I'm storing the right value in the left element. So HA is HA plus 1. And then the temporary value will be stored in HA plus 1. There is a trick in Python how you can swap two variable values in one line of code, but these are just Python details that we don't use. So you can do it more or less the same, say in Java or C++. You just need to look at how to build your loops. And we're not taking advantage of some Python tricks of how we can do this. It turns out you can improve this even a little bit, or I'm asking you first, what's the O complexity of this algorithm? I have two loops, both running to n or n minus 1. Maybe you can tell me in the chat what the O complexity of this bubble sort is. O of n squared. So not n, O of n squared, because I have a loop that runs n times and inside n minus 1 times. So O of n squared. What I also told you before is when we did the first pass through our data set, we were able to move the largest element to the rightmost index. And when you do a second pass, so when you complete the inner loop again, and you do the next pass of the outer loop, you're moving the second largest element to the right. So it turns out you don't fully need n minus 1. It's actually n minus I minus 1, because as I grows, I have kept moving elements, the largest elements, to the right. But this turns out it's still O of n squared. It just leads to a somewhat speed up, but not too great. But let's test it now. We have our data, which is something like this, just from the recommender. We can run bubble sort now on the data. You see A will be manipulated directly. So we manipulate A. We're not returning anything, but we're manipulating it. We can see the data is now sorted 1, 2, 5, 9, 20, 30, 100. So this is our bubble sort. It's a fairly easy algorithm, but we see it's O of n squared. Not too great. So the worst time complexity of bubble sort is O of n squared. The one we have implemented also has a best case time complexity of O of n squared. If you improve bubble sort a little bit, the best time complexity will be O of n. That's actually something in the coursework you will see later, how we can improve this best case a little bit. But the average case time complexity is still O of n squared. And the space complexity is O of 1 if implemented correctly. And algorithms that have a space complexity of O of 1 are algorithms we often call in place. So in place is a term that refers to algorithms that have a constant space complexity, not just in sorting, but in general in algorithms. And the algorithm is stable. Now you're wondering, what is a stable sorting algorithm? Let's discuss this. When we have a data set that we are sorting, and we have duplicate values in there, so repeated elements. Imagine the data set from before, we had a 2 in there. If we had multiple 2's in there, so we had repeated elements, then we would actually wish that we preserve that order of the elements that have the same value. Say we have a 2 somewhere in the data set and a 2 later. We want to keep them in that order. We want to sort, but we want to make sure that the first 2 will also be before the second 2 in the result. We don't want to mix them up. For integers, this doesn't make a difference, but maybe imagine these are more complex objects and you're sorting them based on some criteria or some of their properties. So stability is something that is oftentimes desired. And the bubble sort is stable. We will later see more sorting algorithms that are stable and some that are not stable. And why is So there's one visualization of stability here, but you can read this online if you wish. And we will look at a concrete example of more complex objects. Imagine we have a string. And this string, we want to do a word count. So I'm trying to read out this tongue twist. It's something like how much wood would woodchuck chuck if woodchuck could chuck wood. And we do a word count, we will see something like this. We will have tuples now. So we don't have just single integers, we have tuples as the elements. And the first tuple is how. How appears once in here. Much appears once in here. Wood appears twice, which is here and there. Woodchuck appears twice. Chuck appears twice. If appears once. And could appears once. So this is my data set now. I have tuples. And I can sort this tuple first in a lexicographic way based on the string. So I'm sorting these tuples based on the string. And the consequence would be, so we're sorting this in an ascending way. Chuck is the first word, which had an integer of 2. Could comes next, which has the count 1. How, if, much, would, woodchuck, would. So these are just sorted alphabetically or lexicographically in order to be technically correct with the associated integer. Now I want to sort this again. So the result I have from the first pass, I have this sorted lexicographically, and I want to sort this on top now based on the integer. And with a stable sorting algorithm, what I want is I eventually have first, and I'm sorting this now descending. So I want the 2 integers first and then the 1 integers. And the stable sorting would mean I have these 3 entries which have integer 2, but among this group of the integers 2, I want to keep the lexicographic sorting because before I had sorted my data set based on the string, and that order I want to keep preserved among the groups. So one group has integers 2, and then I want chuck, would, woodchuck, and in the next group where I have the integer ones, I also within that group want to preserve the lexicographic ordering. So it's could, how, if, much, would. And this is something that a stable sorting algorithm like bubble sort will give to me. There are unstable sorting algorithms. What they do is they will still give me a correct sorting result. So I first have the pairs that have integer 2 and then the ones that have integer 1. But within these groups of 2s and 1s, I don't preserve this lexicographic sorting. On some use cases, you may want this to be a property. In some use cases, maybe it does not matter. But maybe you know this from Excel when you have a table and you sort it based on different criteria. First one criteria, then the next one. There, oftentimes you want stable sorting. Otherwise, your Excel sheet will not look very nice and not help you in solving your problem. Is this something you've noticed in Excel when sorting based on multiple criteria that you preserve, that you want to preserve the ordering in a stable way? Maybe just give me some signal, positive or negative, if this is something you have come across before as an end user. Yeah, so that's what stability means. It doesn't really matter if you just have integers that you store, and if you have the 2 or the other 2 first, doesn't make really a difference. But if it's more complex objects, like here these tuples or other objects, and you're doing sorting based on some of their criteria, then it does make a difference. When you take or when you study sorting algorithms, there are 2 more that you can find in the literature: selection sort and insertion sort. These are two, again, relatively simple sorting algorithms, but they are also both extremely inefficient. Selection sort has a worst case, best case, and average cases of O of n squared, has a space complexity of 1, so it's in place, and it's unstable. So really, it doesn't look that useful. Even our bubble sort was maybe more useful because the bubble sort was at least stable and had, if you implement the bubble sort, better best case time complexity. The insertion sort is stable, also has a space complexity of O of 1, and the best case time complexity of O of n, but worst case and average is O of n squared. I'm just putting here these fact sheets for these two algorithms, selection sort and insertion sorts. It turns out in a lot of algorithm classes, these two sorting algorithms are discussed in detail. I honestly don't know why. Because we've already seen an inefficient algorithm bubble sort, so it doesn't make much sense to me to discuss two more that are inefficient. Maybe they're interesting to study and see how they work. In case you want to study them, take a look into the book or lots of videos on YouTube that visualize algorithms for you. But I think we want to spend more time on efficient sorting algorithms. So maybe let's skip selection sort and insertion sort. And I honestly don't know why a lot of professors spend so much time on these two, because we've done the bubble sort. So let's actually do something more efficient. And we will now see two sorting algorithms that are highly efficient. And we will come back to these terms bottom up and top down. We've seen this just before when we looked at dynamic programming, speeding up recursion, and bottom up and top down are two more generic design principles for algorithms. And the merge sort is highly efficient and it works bottom up. And I'll tell you what it does. What it will do is we have an unsorted list of entries, n entries. And this unsorted list will be divided into n sublists. So we will have n sublists. Each sublist only has one element. And if you have a list with one element, that list is sorted. And we have n many of them. And the merge sort will try to repeatedly merge small sublists into larger sublists. Because you have two lists, each has one entry, and you merge them, you can just check which entry is larger than the other one. And then you have a list of two. And then you can try to generalize this merging, and you merge and merge into larger sublists that are sorted. And I'll show you what this concept looks like. There are a few slides here from the book. Imagine we have a data set that looks something like this. We have entries 85, 24, 63, 45, 17, 31, 96, and 50. We can break this. So we somehow need to break this now into smaller lists, but we're starting. Because we cannot just arbitrarily say, suddenly I have n sublists, but rather I need to somehow need a repeatable process to break it. I can say I can split this data set into left and right. Now I'm trying to sort left and I'm trying to sort right, and then I merge them together because merging of two sorted lists is fairly easy. And that's something we will also visualize later. But this sublist is still 4 entries. I'm still unable to sort it directly. So I can break it again. I can break it into a left sublist, which is 85 and 24, and 63 and 45. So this one here just got broken. But this one here is still too big because I need two single lists, which are one list is 85, and I have the 24 here, which I also want to make a separate list. So I have 85 and 24. Each are single lists now. And then I can try to merge them together because I have the 85 and the 24, and I have two lists with two single entries, and I just merge them because the 24 is smaller than the 85. That's something I can check because I just have two lists with one entry each. So the 24 and the 85 are now merged into a sorted sublist. But I still have my 63 and 45. Still a sublist I need to merge. I need to first split into a 63 and a 45, which I can do here. I have a 63 and a 45, and I know 45 is smaller than 63, so I put them in the right order. So 45 and 63 is now the next sorted sublist, and the one from before is a 24 and an 85. Now I can try merging these two sublists. I have a 24 and an 85 in the first list and a 45 and a 63. So I can merge this. I can look at the first element of both lists. From the first list, it's a 24. The other one is a 45. I take the smaller one, which is 24. Then I move the index in the first list to the next element, 85, and my other sublist is still not touched, so the index still points to 45. Then what is the next element, 85 or 45? Obviously it's 45, so I take 45 next and move the index to the 63. Now I have 85 and 63. Which one is smaller? 63. And now I have one element, it's the 85. So I have just sorted the left sublist of my whole data set because it looked something like this: 85, 24, 63, 45. By keep splitting it and then merging it, I have achieved a 24, a 45, a 63, and an 85. Now I have to do the same procedure with the right sublist from the very beginning. I again have to split this into smaller and smaller sublists and then keep merging them recursively. And what I will have eventually is I have this sorted sublist and I have this sorted sublist once it's sorted, and then I merge them again. And then the whole data set is sorted. So assuming now we have done all these steps on the right sublist, which was 17, 31, 31, 96, and 50, sorted it's now 17, 31, 50, and 96. And now I have these two sorted sublists, and I can again merge them by always picking the smallest element, 24 or 17, it's 17. Then 24 or 31, it's 24. 45 or 31, it's 31, and so forth. So I just keep doing the merging, and eventually I have sorted my data set. So we need to implement two parts. We need to implement the merging, and we need to implement, so we need a procedure that can merge us two sublists, and I need a procedure which does all this splitting, because I somehow need to split the original data set into smaller ones. Let's first look at what the merging could look like. There's a very good visualization from the book, and it's something like I have two sublists, S1 and S2, and I have started merging them already, and they are sorted. So a 2, 5, and 8 have already disappeared. That's why they're in white. And the 3 and the 9 have already been taken. So these 5 entries are down here, 2, 3, 5, 8, and 9. And I have now an index I that refers to the next element in S1 that has not been taken yet, which is the index 3 at 11, entry 11. And the second list, S2, I have index J, which refers to element 2, which is a 10. So I take next the 10, where index J refers to, and I'm putting this here after the 9, it's a 10. And I'm increasing the index J by 1, and it will now point to the next element in S2, which is 18. How can this be implemented? What you always need to do is you need to put initially your index I at 0, j at 0, and you're writing in S, and S has just the length of S1 and S2 combined, and the element you're currently writing on in S is just indexes I plus j, because you have index I from the first list and index j from the second list. And then you pick the smaller element, either the one at I or the one at j, and you keep increasing the index. Plus, you need to have some special case once you have finished reading from one list that you only keep reading from the remaining list. How can this be implemented? This is your task in the coursework. What you need to implement is a function merge, and merge has 3 parameters. You have a list S1 and S2, which are these sublists, and you need to write in S. So it's very important. You're not returning S, but you are getting a reference to S, which already has the right size. So you don't need to change the size of SS. We will later see this when we use merge from our merge sort algorithm. It already has the adequate size. So all I need to do is I need to write into S at index I plus j and either take the element from S1 or S2. It's something you can implement in less than 10 lines of code. This is your coursework. And speaking about the coursework, this is problem 11.2. You need to implement merge and we use it within merge sort. I will show you next how you can implement merge sort, but it needs a helper function, which is the merge function. And this is your task to implement, but it's just a few lines of code. It's not that difficult. And it's already visualized here quite well that you need your indexes I and j and read. So you need a loop to go through your indexes and read either from S1 or S2 and increase the indexes and write in here and make sure you don't have a bug if you have finished reading from one of the lists. So you keep just reading from the next one or from the second one that is sorted anyway. So this is your task in the coursework. Not sure if you have seen this in Python. If you want just an empty function or empty method, in Java or C++, you would just use opening and curly braces. Since we don't have this in Python, you just put a pass. You intend correctly, but you just put pass, and pass just means empty body. So when you implement merge, also make sure to remove the pass and just write here, it's just less than 10 lines of code if you implement it well. And merging is the helper. What we need to do now is the actual merge sort. And this one can be implemented fairly easily. And I'll show you this in my live session. What I have just done is I have just copy pasted my implementation of merge in this interactive session. I'm not showing it to you, and that's why I've just cleared the screen or cleared the terminal, so you'll not see my merge. It's your task to implement it, but since I have it, I know that it works, and we can now implement merge sort. For merge sort, we are passing a list S and we manipulate it directly. And the concept we have seen before is actually we just split S into left and right recursively. At one point, left and right is sorted, and we just merge this again. And we need to know how many elements we have in S. And if we have less than 2 elements, then we are just done, then we are returning. So this could be a special case that you're calling merge sort on an empty list, there's nothing to do, or you are calling merge sort on a list with 1 entry, so we're also just returning. Return just means abort, because we're manipulating S, so we're not returning S. But there will be recursion. So this edge case here will be needed again when we call, when we do these recursive calls. And now what I have is my S, and I want to split it into left and right. So I want to have S1, which are all the entries from the beginning up to mid. The middle index, we will see very soon how we can calculate the middle index. So mid is to be shown, and mid is excluded. So we can also write 0 up to mid, but if you leave the 0 out, it's implicitly there. And S2 is everything as from mid. We could put in n, but you can also just leave it out, and it takes all the elements as of mid. And mid is here the upper boundary that is excluded. So everything before mid is taken, and here everything as of mid, where mid is included. The middle index is just n divided by 2. And remember, we want an integer division in Python, so we divide n by 2. And now we need recursion, we need merge sort. I am splitting S into S1 and S2, and it's divide and conquer. I'm unable to sort S1 and S2 directly. So let's use divide and conquer that S1 is sorted, S2 is sorted, and all I want to do is I want to merge S1 and S2 into S, the original parameter. And it turns out I'm done with the merge sort, because I'm sorting the left one, the right half, and then I'm just merging them. And these are the recursive calls, and this will keep going recursively until I have single elements or new lists with single elements. And then I'm merging single lists together into larger lists, and eventually it all comes recursively back until the left one is sorted, the right one is sorted, and then I have these sorted S1 and S2, and I merge this into S. Are you surprised that we can implement a merge sort just in a few lines of code? Because we've looked at these plots before. If you're surprised, send some reaction. Maybe green one, you're surprised, red one, you're not surprised. Obviously, what we need is the merge helper, but this is something that you need to implement as part of the coursework. But it turns out the merge sort here is fairly easy to implement because we can use divide and conquer. And now let's test it. We have a data set S, or before we called it data, and we call merge sort on the data. Let's see if the data was sorted. Yeah, was sorted. So it works. And all you need to do is at home implement merge, which is a few lines of code. And it makes sense to split this into a separate function just in order for this algorithm to be understandable. And here's the implementation of merge sort. There's no implementation for merging in the slides, but that's the coursework. Now, what is the running time complexity? Do you think, maybe without looking at the next slide, what do you think could be the running time complexity of merge sort? If you have any guesses, send them to the chat. A lot of students write n log n, and that's correct. And I'll tell you why. So the worst case is n log n, best case and average is also n log n, but we care about the worst case typically. It is stable. That's something that is very helpful, but the space complexity is O of n because we also have all these recursive calls. Why is it n log n? It turns out we have some constant work here. We need to split something and whatever, like this stuff here, or we calculate this mid index, we have two recursive calls. So this is t of n half, because it's the half. It's t of n half. So 2 times t of n half plus merging all of these elements. So the recurrence relation is t of n is 2 times t of n half plus n. And I told you last week when we looked at recurrence relations, we started with this generic algorithm pattern, and I said we would see it again. That's what we have done today. We are doing something on the left half, on the right half, and finally we're doing some combination work on all the n elements. And we know how to solve that recurrence relation. And t of 1 is 1, because if we just have one element, we're just aborting. So the worst case is O of n log n, and you can solve this recurrence relation either manually or you can use the master theorem. There is one more sorting algorithm that is super popular, and it's called quicksort. In quicksort, we will look at its complexity later, which is a little bit more problematic, so to say, or more difficult to assess and comes with some consequences. Yet it's a super efficient sorting algorithm. It's again a divide and conquer algorithm, but it works top down. And what it does is it starts with looking at your whole data set. And it selects a so-called pivot element from the list, which is one of the elements. You have an unsorted list. And what you want to do is you want to partition the other elements into two sublists according to whether they are less or greater than that pivot element. So you just pick one element and say that's the pivot, and I want to have one sublist of all the elements being smaller than the pivot and all the elements being greater than the pivot. And then I'm again doing this recursively on the left and right. That again, for the left sublist or for the first sublist, I'm doing the pivoting, and for the right one. And again, recursively, and like this, I'm doing a top-down sorting. But we will now have a 10-minute break, and then we continue with this. So this is how quicksort works, and we will visualize it now, and then we will implement it, and we see that it isn't that difficult. I told you we're picking one element as the pivot. And in the simplest quicksort implementations, the pivot could be just the first or the last element. The pivot from now on is visualized in bold. So what we're doing is we're picking one element as the pivot. We will later discuss if it's always smart to pick the left or the rightmost element and what consequences could be. But for now, we just pick, say here, the rightmost element in bold. This is the pivot. So we are creating two sublists of elements that are smaller or greater than the pivot. So the left sublist would be the elements 24, 45, 17, 31. They are smaller than the pivot. And the other elements are greater than the pivot. So 85, 63, 96. We're not sorting here, we're just picking the elements, we're going linearly through and say there's an element, that element is smaller or greater than the pivot, and we create these two lists. Now, we do this recursively again. We have this list here, and we pick again the rightmost element, which is a 31, and we have a pivot that is 31. So the 24 and the 17 are less than the pivot, and the 45 is greater than the pivot. Now, this left one here, it's two elements, so we need to do this again. We pick the 17, the pivot. There's nothing smaller than the pivot, but the 24 is greater than the pivot. So we have these two lists here. In an empty list, we are done. And if we have a single element in a list, we are also done because there's nothing to pivot or sort anymore. Then up here, where we had the 31 as the pivot, we had the 24 and the 17. So we are now on this next figure. So we see when we are putting this together down here, the 0, or the empty one, the 24, and the pivot, what we do is we pick the empty element, which we don't pick because there's nothing, then the pivot, and then the element from the right sublist, the 24. So it's 17 and 24. This 45 here, we are also aborting because there's nothing else we need to do. And then we are putting all of this together. So we had this sublist here, and we had the pivot 31 and split it into one sublist 24 and 17, and the other sublist 45. The 17 and 24 are now in order, and we put all of this together again by picking the left list, which is the 17, 24, then the pivot, and then the right one, which is the 45. We are doing this procedure exactly the same for the right one here, the 85, 63, and 96. So eventually we get a 63, 85, 96. And then we're done. We have sorted the whole data set because the left sublist is the 17, 24, 31, 45, then the pivot 50, and then the 63, 85, 96. So this is the quicksort, and we will later discuss why it's actually considered to be quick. But we'll implement it together now. This time, I will fully implement it for you. There's nothing that you need to do as part of the coursework to have it running. Let's see how it works. So we're saying if the length is less than or equal to 1 or less than 2, as before. So if we have 0 or 1 elements in S, we're aborting. This time, the algorithm works slightly differently. It does not manipulate the S, but it returns the S, or returns a new list. We will later see why this is a bit more convenient when implementing a simple one. This quicksort implementation is very simple. There are far better ones, but it just shows you the essence of quicksort. So we have a left sublist and a right one, and we need to split these elements based on the pivot now. The implementation that I'm using here is we are using the leftmost element as the pivot. In the figures before, it was the rightmost element, but we're just picking either the leftmost or the rightmost element for now as the pivot, but doesn't make a difference whether it's the leftmost or rightmost element. And now I need to go through every element in S, and I need to check, is the element greater than or equal to the pivot? Because there could be also duplicate elements. So the pivot may be there. There may be more elements that have the same value as the pivot. And we are appending this to the right. So the element is greater than or equal to the pivot. So we put this into right. Otherwise, we put it into left. Then we have now split this into left and right. So we need a recursive call on the left one again. And this will return me something. Because we always said now we're not manipulating the parameter, but we are returning something. So I'm storing this in left again. So what I'm saying is I'm splitting my data set into left and right. And then the divide and conquer approach is do the same one again for the left and do the same one again for the right one. And eventually, I will now have a left and a right half sorted, and I need to glue it together. And in order to glue it together, I can use this plus sign for a concatenation. So I'm concatenating the left and the right list, but it's a little bit more complex because I need to keep track of that pivot. And remember, I've said I'm always using the leftmost element as the pivot. And the pivot does not need to go into the sublist. And now I'm taking always the leftmost element initially as the pivot. So when I merge this together, I have the left and the right sublist, and I have the pivot element. But syntactically, this will, or when you run it, it will not work because left is a list, right is a list. So I need to put pivot in a list on its own, and then I can concatenate this. One more thing is, well, we've checked here if the element is greater than or equal to the pivot. I said there could be duplicate elements of the pivot, but there is the actual pivot as well, and we have not really excluded here at that moment. So we say the first element that we find that is greater than or equal to the pivot is the actual pivot. Because I say the pivot is element at index 0, and when it appears that I find an element that is greater than or equal to the pivot, then I'm putting it in right. But actually, I don't need it further. So down here, when I'm calling quicksort on the right, I'm not calling it on right, but on all elements starting index 1, because index 0 is the pivot element, but I have this already in my local variable. So I don't need to pass this into the recursive call. So I'm putting here a 1 further. If you can think about how to change this on your own, if you say the pivot is the last element, not the first element, then you have to think about how you would change this here, but it's just a minor change. You just have to change the slice here and think about if the pivot is the last element, where would it appear in right based on this condition and exclude it from there. It's just a tiny difference in here if you choose to pick the largest or the rightmost element. So let's run it. We have our data. And then let's call quicksort on the data. And it returns now something. So it doesn't manipulate the parameter, but returns something. And what it has returned is also sorted. So what I have to say is this is a very simple initial quicksort implementation. It's not very memory efficient. And I have these sublists and I keep adding elements and they may resize. So this is not the fastest quicksort implementation possible, but it's one that fits on one slide and shows you the essence. So that's the idea of the quicksort. Why is it called quicksort? Because you would assume it runs very quickly. What do you think is please, without looking at the slide, what is the running time complexity of quicksort? Any guesses what you think a sorting algorithm that's called quicksort, what would it be? What complexity would it have? We've seen before merge sort was already efficient, so that was n log n. What could it be? Some students are suggesting n log n. And it turns out, well, one student guesses the best case is O of 1. Well, that would be the case if you pass one element and you have this. But if you pass an unsorted list, or you would maybe think the best case could be passing a sorted list. One student suggests it's O of 1. It could look like this, but we will study if that's the case. One student wonders, could it be O of n? Because O of n appears faster than n log n. These are all very good guesses. And that's why the quicksort is a little bit more complicated than the merge sort. It turns out the quicksort has a worst case time complexity of O of n squared. Why is that the case? It has to do with the pivot. Imagine I'm picking a pivot here, the left or the rightmost element. Say here the rightmost element. And with these examples, it's splitting the data set very well. But imagine what would happen if you pass a sorted data set here. Imagine we're passing this to quicksort, and the rightmost element, the 96, is the pivot. What would happen if I pass this to quicksort? If you see what could happen, send it to the chat, turn on your mic, or send some reaction. If you think you notice what can happen if I call quicksort on this sorted set here, or sorted list, and the rightmost element is my pivot. What happens is your left list will be all the elements except the pivot, and your right list would be empty. Because all the element, if this is sorted and 96, your rightmost element is the pivot, you put all the elements into the left one and nothing in the right. And the same would happen if you pick the leftmost element as the pivot. Then everything would go in the right, nothing in the left. And it turns out, and this is something that sounds first of all strange, if you call quicksort on a sorted data set, it takes O of n squared. So quicksort behaves super bad on a sorted data set. If your data set is not sorted, quicksort runs in O of n log n. So the best case and the average case is O of n log n. But the worst case is you're calling quicksort on a data set that is sorted already. And this leads to O of n squared. So it sounds strange, calling something on a sorted data set and it doesn't work well. Now you could have maybe a check before and check, is it sorted as a pre-check, and then not run it. You could do this in O of n, but this effect still happens if it's almost sorted. Say it's almost sorted and you split these two into very different sizes. Then your quicksort will still be super slow and not quick at all. Good implementations of quicksort, for example, run in O of log n. The initial quicksort is unstable, but there are stable versions of quicksort already. And the space complexity of the O log n has to do with these recursive calls, because you would have in the order of log n many recursive calls when your data set can be split well into a left and right that are about the same size. Then you have a depth of your recursion tree of about log n. But our implementation here is not that great because we create these helper lists and we keep resizing them. But this just shows you the essence of quicksort in a very simple way. But still, quicksort is O of n squared and not O of n log n. Even though this O of n squared appears rarely. And that's why there's another coursework problem, 11.3, in which you have a different task. You're tasked with implementing a randomized quicksort. A randomized quicksort would not pick the left or the rightmost element, but a random one. For example, the 24, the 31, but it's still n squared, O of n squared, because in the very worst case, your randomized quicksort would just pick you the largest element, because maybe you have this data set and it just picks you, the randomized one picks you the 96, and then you're still not performing well. So I found there was some algorithm coursework from Princeton, and the instructor there wrote, the professor there wrote that the algorithm has, so quicksort is O of n log n, but the terminology used in this reference was that quicksort has a worst case expected running time of O of n log n. So worst case is still O of n squared, but the worst case expected one is O of n log n. If you do the randomized quicksort may still be O of n squared because you're still unlucky picking a random element. But that is extremely unlikely as it's argued here. So this is something you can also read. So the randomized quicksort is used in practice, and this one has a worst case expected running time complexity of O of n log n. Makes a difference to worst case time complexity. So this is another coursework problem, and you would just amend this implementation here to pick one of these n elements randomly if you wish. So give a try and see how you can amend this here. There are many more sorting algorithms. There are, in fact, many variations of quicksort, merge sort. There is a stable quicksort, and there's all sorts of variations of these algorithms. We saw quicksort is a top-down one, and the merge sort is a bottom-up. But there's even, I don't know, a bottom-up quicksort and this kind of stuff. So lots of variations have been proposed because sorting is one of the best studied topics in computer science. There are more sorting algorithms like heap sort. Heap sort is very interesting. Heap sort has a worst, best, and average case complexity of O of n log n and constant memory usage. So in place. And this is really cool because our quicksort we saw has a space complexity of O of log n and it's unstable. And the merge sort has a space complexity of O of n. And heap sort has a space complexity of O of 1. So it's constant because it does some tricks with the data set. But in practice, it performs slower by some constant factor than a well-tuned quicksort or a well-tuned merge sort. Why is it called quicksort? Because in practice, quicksort runs the quickest in terms of the expected complexity as well as of the actual running time if it's well tuned. And that's why it's called quicksort. And we saw that complexity is important, but eventually running times are also important. Good running times are often a consequence of good complexity plus some tuning then. I've mentioned Bogosort when we started today and said it just does random shuffling and you hope you have sorted. And there are lots of variations, and it's still an active research topic today for specific sorting problems. There's a very interesting video. It's from like 2007, 2008. So it was the time I was just finishing high school and I saw the video. Obama was running for president. It was in the early stages of his campaign. So he was a senator and he visited companies because he tried to get the nomination from the Democratic Party. And Obama then visited all sorts of companies and he visited Google. And Eric Schmidt was the chairman of Google at that time. And what they did was Obama was interviewed at Google for a job. And they asked him obviously lots of political questions, but they also asked him which sorting algorithm he would pick. So you can see how Obama would answer because Eric Schmidt said that getting a job at Google was more tough than becoming president. And that's why they challenged Obama with a couple of questions. It's a very good video. Take a look at it. I found it very funny and appeared around the time when I finished high school and started studying computer science. Now, I asked you before where you would guess a quicksort would run. And we saw a quicksort is even O of n squared, even for unlikely, but expected n log n, at least the randomized one, but still n squared. Can we do better than n log n? And it turns out that's a complex discussion. It can be shown that sorting cannot run better than n log n if you use comparison-based sorting. All the sorting algorithms today we have studied run based on comparing elements. Is one smaller than the other or something like this? Does the bubble sort, the insertion sort, the selection sort, the merge sort, the quick sort. And it has been proven decades ago that when you have a comparison-based sorting algorithm, it cannot run better than n log n That's why it is omega of n log n. It's a lower boundary for the worst case. There are some other sorting algorithms that are not based on comparisons. There's, for example, the bucket sort, which tries to put your data into different buckets or distribute your data into a number of buckets. And it turns out such a bucket sort is O of n under very specific circumstances and makes certain assumptions about your data. But this kind of stuff has rare use cases. I think most of the sorting we do nowadays is comparison based. And this bucket sort makes some very specific constraints and works only under very specific circumstances. So it's important for you to remember comparison-based sorting is constrained to n log n, so omega n log n, not sorting in general, because this is often wrongly taught or wrongly remembered that people think sorting could not be done better than n log n. Well, it's comparison-based sorting, what we do most of the time. But there are other sorting approaches like bucket sort, which would run in O of n, but with very specific circumstances and assumptions. But we typically do comparison-based sorting, and there it's omega n log n. So you see, finally, we not just need O's, we need the thetas today for the master theorem. We need the omega for here the comparison-based sorting lower bound. Eventually, we need all of this theory we taught a few weeks ago. Now comes some interesting questions. The bubble sort, it really looks like bubble sort is so simple you would never need it. And a lot of professors actually teach this. I was also taught that when I studied that bubble sort is just, a toy algorithm, you would never need it. And I've asked myself many years ago if bubble sort is actually useful. And it turns out it is. I found there was a very good discussion on Quora. So discussion I came across many years ago because someone asked when you would actually use bubble sort. And it turns out bubble sort is actually quite helpful. For example, if you have a data set that is almost sorted and you just want to finish sorting it, maybe you just need a few passes of your bubble sort and it's sorted. So if you have an almost sorted data set, it's fine. Or maybe you have a data set, but you don't need it fully sorted. You just want to have a better sorting, but not perfect sorting yet. Maybe just a few passes can run very efficiently because we saw merge sort is n log n, creates a lot of work. You need to have all these recursive calls. You have quicksort is anyway a particular adventure, since it's O of n squared if you're unlucky. And it's a lot of work that gets done, but maybe you just want to have a data set and sort it a little bit better, not fully sorted yet. And for this kind of stuff, bubble sort is actually used in practice. For example, in graphics and game programming, where you have a game with a certain number of frames, say 30, 40 frames per second, and you have limited time of what you're able to do in, say you have some pixels and you keep moving, but the frame you're rendering doesn't need to be perfect sorted yet because just, a few milliseconds later, you're rendering the next frame. But maybe you want what you're visualizing, you want this to be almost sorted, and you want to have a few passes within the next few milliseconds to, again, sort it a bit better based on the changes in the environment, especially if these lists don't change much between frames. And then it turns out that maybe a single pass or a few passes can help a lot to maintain that order more or less. And the bubble sort is extremely fast. This is something that I came across many years ago. And a few years ago, I had a chance to have a chat with someone who did lots of graphics work at Apple. And somehow, a retired guy, I have him on my LinkedIn if he listens. So, sending all my best to the Silicon Valley. And I had a chat with him if that was actually true. And he said, yeah, that's exactly what he did many years ago at Apple for some graphics rendering, used a few passes of the bubble sort in each frame and maintained almost sorting or sorted the data a bit better. And then just because these lists were not changing much, that actually worked. So what I want to say is the bubble sort is not completely useless. It has some useful use cases, but they are limited, but it's just wrong that it's totally useless. And that's why when you work in industry on real problems, you need to pick the right algorithms, and you need to, obviously you will come up with new algorithms, but also use others' algorithms, pick the right ones, customize them. And it's not always just maybe the quicksort or the merge sort you'd be using. You need to look at all the constraints, maybe real-time constraints, like in a video rendering game. And then for some cases, maybe the bubble sort is actually helpful. We will do a last few slides for sorting in Python. In Python, we have this sorted function that can sort us a data set. We have used it in the last lecture. So when we discussed binary search, we needed sorted data. And this sorted function in Python is actually not using quicksort or bubble sort, but it's an algorithm that is called timsort, and it's a hybrid stable sorting algorithm that was derived from merge sort and a combination with insertion sort. And this one was designed with the wish to work well on many kinds of real-world data, was designed by Tim Peters, and is used in the Python programming language. Feel free to read about it if you wish. The worst case, average case is n log n. The best case is O of n. The space complexity is O of n, and it's stable. So this is the one that was built for the Python ecosystem. And mentioning Python, we will now look at how you can actually sort something in Python. Obviously, we have our data set like this one here, and we want to sort it, and we get it sorted. But you can do more in Python. And before, we've seen, for example, these, if you remember, we have seen these tuples when we counted words in a text, and we wondered how can we sort based on different criteria. And here in Python, we can do something quite interesting. We can say, introduce a data set. These are tuples now. And we have the first entry of a tuple is a string. The second entry of the tuple is an integer. And we have now such pairs. So red 1, blue 1, red 2, and blue 2, something like this. And now what happens if I call sorted on data? We will get something, but we would need to read the literature, the documentation now. How does it actually sort this? We can actually control this. What we need is from the Python operator package module, we need the so-called item getter. And I'll show you now what we can do is, what you can always do in Python is, in the command line, you can put a question mark behind a function, and then you get its documentation. So sorted question mark. Not sure how this would run in an IDE, but in an interactive environment, you would just put a question mark, and you see the iterable is something we're iterating over the data. That's mandatory, and it has some more parameters. We can pass a key, we can have a reverse. So we get at least a little bit of documentation. And we can call now sorted on data, and we can say, because I have two entry where I have two values per entry, I could specify, do I want to sort based on the string or based on the integer? And for this, I need the item getter. And in Python, the item getter, what it would do is, item getter 1 would mean when I sort a data set, the item getter 1 would mean it looks at the elements, and it opens the elements and looks within the elements at the second entry. So index 1, because we have this entry, we have index 0 is blue, index 1 is the 1, 0, 1, and so forth. So we would say I want to sort this now based on the integer. And now I get this in an ascending way. So red and blue, so it's 1 and 2, 1 and 2. But I could also reverse this. And reversing means I'm sorting this in a descending way. And obviously I can put in a 0 in here. So I'm sorting this based on the string. So red, red, blue, blue, because all of this gets sorted based on the string, and I can reverse it or not. So if you have multi-value entries, you would probably be able to take advantage of such an item getter quite efficiently, and you can either reverse or not. Just some Python detail, but many of you write Python code, so it's, I think, good if you have seen this. This is sorting in Python, and we're now done with sorting, and I've shown you the coursework. Since some students don't always follow the iLearn notifications, as we saw today, I had sent you that next week we do not have labs and we do not have a lecture, because next week I'm at a conference in Jordan. And I will be away all week long. So we are meeting again on the 16th with our usual schedule that we have lab sessions from 8 o'clock to 1 p.m. and then another lab session from 2 p.m. to 3:30. And then we have one lecture on the 16th at 3:45 to 5:15. And in that lecture, we are starting with trees. We will probably need two lectures for trees. And trees are another data structure, and we will see how we can define trees and have binary trees and store data in there, walk through the data, sort trees, and we will also apply this to machine learning, and we will see how we can learn our own decision trees. Because decision tree learning is one algorithm from machine learning. And since many of you study AI, and those of you who don't study AI still need AI, we will apply trees to a machine learning problem. But for this, we need two lectures. So in 2 weeks, we are starting with trees and probably make the first 3 entries in the decision trees another time. So next week, we're not meeting. So I'll see you in 2 weeks again. However, if you have any questions in the meantime, be it on the coursework or the lecture, feel free to send an email, and I'll try to respond as quickly as possible in the next 2 weeks, or you will see me simply in the lab in 2 weeks. If there are no more questions, if there are questions, maybe just raise your hand. And if there are no questions, then we are done for today. And I wish you a great weekend. Enjoy the coursework and see you in 2 weeks. Bye-bye.